In this tutorial, I'm going to talk about the capabilities of PuMA in terms of detecting the orientation of a material. So depending on whether you're running C++ or Python or pumapy basically, you're going to have access to different capabilities. So I want to clarify what you should be using. So starting from pumapy, the only orientation method that we've implemented in this is the one based on the structure tensor. The structure tensor is an image processing technique that is able to detect the orientation of minimal change of gradient in terms of the grayscale values. So I'm just gonna go ahead and press run for this one, and as it produces the results, I'm gonna discuss about them. So the first thing is I'm gonna import a 3D TIFF, which is from the datasets that are currently coming with PuMA, and specifically is the one that is the 200 cubed fiber form, and then I'm gonna volume render it. And so there it is, volume rendered it already. And in this rendering, I've intentionally left the grayscale intensities noticeable so that I can basically give you a feel of what the structure tensor is looking for. So if you look at, for example, along this fiber, you can see that the grayscales change the least, for example, inside the depth along this direction. So the structure tensor, what is computing is the gradient of these grayscale values, and then it's looking for the minimal change. So basically the minimal change will be roughly oriented along the fibers. So I'm gonna close this figure and let the solver run through the compute orientation ST, which stands for structure tensor. The input that you need to give is the solid phase. And so in this specific tutorial, I'm gonna export the workspace. So the orientation gets automatically appended to the workspace. And so in this case, I've just exported it to my downloads. And then I will visualize it using ParaView. I will import it, and as you will see in the drop down list, you will both see data and data orient, which data will be simply the micro CT that we've imported. So I can threshold it again using the similar cutoff value as I did for inside PuMA. And so as you can see, here is our fibers thresholded, and then I can show the vector field that has been computed by running a glyph filter on top of this VTI. And so for the scale factor, I'm gonna put 0.5 e to the minus 5 in this case, because of the voxel size. And then something else I'm gonna change here is how many vectors to plot, and I will put 300,000. And now ParaView is creating the glyph filter, and it will plot the vector field. And in this case, I'm coloring I will just color it, make it white. So as you can see, this is the automatically detected orientation on the micro CT data. And so as you can see, it's pretty accurate for this specific data set, since the grayscale values are pretty nicely visible. So I will now jump back to the PyCharm project, and I will show you how the next section that I've prepared involves basically running the other orientation algorithms that are only available through the C++ version of PuMA. So just to clarify, whoever is not interested in the C++ part, this will be a bit more advanced than the Python part, and I don't want to confuse anyone, so beware that this will be more advanced. So by the way, this is currently running, so I'm just gonna talk over while the solver iterates. So the first part that I've added over here is the creation of two files that we need to compile our project. So basically, these are automatically created, and these are the CMake lists and the make all file. And then the third one is basically our pumaexample.cpp. So what you're seeing here in the Python script is simply outputting these files that we need for compiling the C++ example. So I will open up these three outputs just to show you how they look. So for the CMake, it just looks like a pretty standard short CMake where you're basically linking your C++ file, which is this PuMA example C++, against the already installed library, which is basically specified over here. It's called libpuma. And then the second part is the makeall.sh, which is a bash file. The only thing that it does is basically creates the build folder, and then it runs the CMake, runs the make, and it installs this PuMA example. So this specific CMake was devised so that it will install this PuMA example all the way inside our Conda environment. So as you can see, I wanted to show you that if you go all the way in depth inside your environment, it will basically be inside the PuMA tutorial, and in the bin we have the PuMA example that I'm currently running. So the other part that I created here is just a function that calls this makeall, and then it runs the PuMA example executable that is created. And then the last one is basically I'm creating the C++ file that is right here. So let me just briefly talk you through what I'm running in this file. I'm running basically the three methods, again the structured tensor, but in the C++ implementation part, and then the other two methods that are the raycasting and the artificial flux. So as an example, I decided to run these three methods on an artificially generated sample of fibers. So in this case, we have the input to the generate random fibers function, and you can basically specify all of these ones are input details about the sample that you're about to generate. So to give you a feel, just to have basically a reference of what these inputs are, I usually reference them go into the documentation of PuMA, and then in here in the search docs I will paste the specific function that I want to run, and I will open it, and then here it's pretty small, but you can see the name of every single input. It hasn't been documented as well as the Python version, but you can still get a feel of what the inputs should be. For example, the sizes first of your domain, the average radius of the fiber, etc., etc. So then the second part is I'm exporting the 3D TIFF for the artificial fiber sample domain, and then I'm also exporting the correct orientation. Basically, since we're generating this fiber domain, we know a priori the orientation. So something that I can now visualize is these two files. So if I drag and drop, it will create an out folder inside which the CMakes, makeall, etc., and also all the files that are generated are output. So I will drag and drop this inside PowerView and select the TIFF file, and then click apply. In this case, let me create a threshold of this. Okay, I'm gonna zoom out, and here is our threshold. Here is our domain, which I need to threshold by the correct threshold here. I'm putting 128 in this case. And here is our fiber domain. In this case, I'm also showing a capability that is not currently part of pumapy, which is the generation of random fibers with specified cross-sectional areas. So in this case, I both used, if I jump back inside the PyCharm, I used the straight flower hollow input to the generate random fibers. So the cross-section, as you can see, is we have a hole in the middle of each fiber, and on top of that, the cross-section, it looks like a flower shape, which is more realistic to how these fibers actually look like. So The other thing that I can import is the correct orientation, which is output inside this VTK file. So drag and drop it inside ParaView, and now I can create a glyph again of this and select this, and let's see how it looks like. Okay, so here is our rendered orientation. Just FYI, I increased the scale factor and the number of samples. And so something else that you need to be aware of is that when you import a TIFF inside ParaView, you need to specify here the custom data spacing to just be 1, so that both the orientation and the TIFF will have the same size. So here is our threshold, and then on the bottom we have the correct vector field that was created. So let's check. Okay, it is completed for the 3 orientation methods. As you can see, if you get these are only warnings. The 3 orientation methods have output the 3 orientation estimations. So we can use basically the correct analytical solution for the orientation and benchmark how the 3 methods perform. And this is what I did in one of the papers that I published. So let me import these 3 orientations inside ParaView as well, and create like glyph filters for them. I will color them with different colors so that we can distinguish. And so there we go. So we have the 3 orientations that have been detected, a plot in the same window. So something else that we also analyzed, since this is not really decipherable like visually, we also came up with the function for comparing the different orientation fields that have been computed. So I would recommend to start with the structure tensor in Python. And so that's the easiest thing to run and the most user-friendly. If you need more advanced capabilities, I would then jump inside the C++. This completes the tutorial about the orientation. See you soon.